Alkaline electrolysis is old, really old. Older than modern electronics, older than commercial aviation, older than the digital grid most of us depend on every day. It uses a liquid chemical electrolyte that has to circulate continuously through the system. It responds more slowly to changing power conditions than newer electrolyzer technologies. It operates at lower current densities. It takes up more physical space. And in an industry obsessed with next-generation breakthroughs, advanced materials, AI optimization, and futuristic energy systems, alkaline electrolysis sounds almost primitive. And yet, despite all of that, alkaline electrolysis remains the most widely deployed hydrogen production technology on Earth. That creates an uncomfortable question for the modern green hydrogen industry. If PM electrolyzers are more compact, more dynamic, and more technologically advanced, then why are so many industrial developers, utilities, and governments still deploying alkaline systems at massive scale? Why are some of the world's largest hydrogen projects still being built around a technology architecture that traces its roots back more than a century? Because the real world does not reward technology hype, it rewards survivability under system stress. And that changes everything. The hydrogen industry often talks as if innovation alone determines who wins. But industrial energy systems do not operate like smartphone markets. At utility scale, technologies are not judged only by elegance or peak performance. They are judged by whether they can survive 20 years of operation, fluctuating electricity prices, financing pressure, maintenance realities, material shortages, infrastructure constraints, and unpredictable utilization profiles. The winning technology is often not the most advanced one on paper. It is the one that banks are willing to finance, manufacturers can produce at scale, operators can maintain continuously, and supply chains can support globally. That is the hidden story behind alkaline electrolysis. At its core, alkaline electrolysis performs the same fundamental task as every other electrolyzer. It splits water into hydrogen and oxygen using electricity. But the internal chemistry is radically different from PEM systems, and that difference changes almost every engineering decision inside the plant. In a PEM electrolyzer, the electrolyte is a solid acidic membrane. In an alkaline electrolyzer, the electrolyte is a liquid solution, typically potassium hydroxide dissolved in water. This creates a highly alkaline environment with a pH above 14. And that single chemical difference unlocks one of the biggest advantages alkaline systems have ever possessed. They do not need precious metals. Inside PEM systems, the acidic environment is extremely harsh. Catalysts and components must survive aggressive electrochemical conditions while maintaining high conductivity and stability. That usually means expensive materials like iridium, platinum, and titanium. Those materials work extremely well, but they introduce a dangerous dependency into the future hydrogen economy. Iridium is one of the rarest industrial metals on Earth. Global annual production is tiny. If PM deployment accelerates too quickly, iridium availability itself becomes a scaling bottleneck. Alkaline electrolysis avoids that problem almost entirely. Because the electrolyte environment is alkaline rather than acidic, nickel becomes viable as the primary catalyst material. Nickel is abundant, industrially mature, globally available, and dramatically cheaper than precious metals. That single chemistry shift changes the supply chain profile of the entire technology. And this is where the Renee Energy Systems framework becomes critical. Because the hydrogen economy is not simply a technology race. It is also a manufacturing race, a mining race, a logistics race, and a geopolitical race. A technology can perform beautifully in a laboratory and still fail at civilization scale if the material system underneath it cannot expand fast enough. This is one reason alkaline electrolysis continues to survive every wave of next-generation replacement narratives. It operates inside an industrial ecosystem that already exists. The materials are familiar, the engineering is mature, the supply chains are deeply established, the maintenance philosophy is understood. And in large-scale infrastructure transitions, familiarity is often more powerful than novelty. The actual electrochemistry inside the cell is elegant in its simplicity. At the cathode, water molecules gain electrons and split into hydrogen gas and hydroxide ions. The hydrogen leaves the cell as product gas, while the hydroxide ions travel through the liquid electrolyte toward the anode. At the anode, those hydroxide ions release electrons and form oxygen and water. The electrons flow through the external circuit, and the cycle continues. The overall reaction is still simple water splitting. Water enters, hydrogen and oxygen leave. But the direction of ion transport is reversed compared to PEM systems. In alkaline electrolysis, hydroxide ions move from cathode to anode instead of protons moving through a membrane. That chemical reversal affects everything from catalyst selection to separator design to thermal management. The physical structure of an alkaline electrolyzer reflects this older industrial philosophy. Instead of highly compact solid-state architectures, alkaline systems use flowing liquid electrolyte circuits. Potassium hydroxide continuously circulates through the plant. Pumps move the electrolyte. Heat exchangers regulate temperature. Gas separators remove hydrogen and oxygen from the liquid stream. The system behaves less like an electronic device and more like a chemical processing plant. And that distinction matters. Because once hydrogen projects move from laboratory scale into industrial deployment, they stop behaving like technology demos and start behaving like infrastructure systems. Infrastructure systems care about reliability. They care about maintenance intervals. They care about thermal stability. They care about operating history. They care about replacement parts. They care about whether operators in remote industrial regions can keep the plant running for 20 years without catastrophic downtime. This is where alkaline electrolysis becomes extremely difficult to displace. Industrial alkaline stacks routinely achieve operating lifetimes approaching 80,000 to 100,000 hours. That is not theoretical. That is field-proven industrial behavior developed over decades of deployment. Failure modes are understood. Maintenance schedules are predictable. Spare part logistics are mature. And lenders love predictability. One of the least understood realities in the hydrogen industry is that project finance often determines technology adoption more than technical performance alone. Developers may want the most advanced system available, but debt providers want systems with known operating histories and minimized technology risk. That creates a hidden competitive advantage for alkaline systems. 100 years of operational data becomes a financing mode. This is one reason alkaline continues dominating large-scale deployments, even while PM attracts enormous attention. When a developer attempts to finance a multi-hundred megawatt hydrogen facility, the financing institutions are not simply evaluating efficiency curves. They are evaluating survivability under stress conditions. What happens if utilization falls? What happens if electricity prices spike? What happens if replacement components become unavailable? What happens if catalyst supply chains tighten? What happens if maintenance costs rise unexpectedly? What happens if renewable intermittency reduces operating stability? In many of those scenarios, alkaline systems still appear extremely resilient. But alkaline is not perfect, and this is where the modern hydrogen narrative becomes more complicated. The biggest challenge facing alkaline systems is dynamic operation. Traditional alkaline electrolyzers were designed for relatively stable industrial power environments. Historically, hydrogen production often operated alongside predictable electricity supplies in large industrial facilities. Renewable energy changes that completely. Wind and solar are variable systems. Clouds move. Wind speeds fluctuate. Grid conditions shift continuously. Renewable electricity does not behave like traditional baseload power. And hydrogen developers increasingly want electrolyzers directly connected to renewable energy sources. That creates a collision between two different system philosophies. Renewables introduce variability. Industrial chemical systems prefer stability. This tension sits at the center of modern hydrogen deployment challenges. PM electrolyzers gained attention partly because they respond extremely quickly to changing power inputs. They ramp rapidly, they handle dynamic operation efficiently. Their compact solid-state architecture is naturally suited for fluctuating renewable power. Traditional alkaline systems struggle more in this environment. Many older alkaline designs cannot operate effectively below certain load thresholds. Ramp rates are slower. The liquid electrolyte system requires time to stabilize thermally and chemically. Gas purity management becomes more challenging during low-load operation. If hydrogen concentration in the oxygen stream rises too high, flammability risks emerge. This is not merely a performance issue, it is a systems integration issue. And systems integration is where many green hydrogen projects quietly succeed or fail. Because the economics of hydrogen depend heavily on utilization. Electrolyzers are expensive capital assets. If they operate only intermittently, the cost of hydrogen rises dramatically because the capital investment is spread across fewer operating hours. This is one of the most important realities in the entire hydrogen industry, and many public conversations still underestimate its importance. An electrolyzer operating continuously behaves very differently economically from one operating only during periods of excess renewable generation. This is why industrial clusters, ports, pipelines, storage systems, and grid connectivity matter so much. Hydrogen systems are not isolated technologies. They are infrastructure ecosystems. And this is exactly where alkaline systems continue finding strength. Because many industrial hydrogen projects prioritize scale, durability, and lower upfront CAPEX over extreme dynamic flexibility, alkaline electrolyzers today often achieve lower system-level capital costs than PEM systems. Large-scale alkaline installations can fall into the range of roughly $500 to $900 per kilowatt, while PEM systems frequently remain higher. That difference becomes enormous at gigawatt scale. At those scales, even modest cost differences translate into hundreds of millions of dollars. And then there is China. The global alkaline story cannot be understood without understanding Chinese manufacturing scale. China has invested massively in alkaline electrolyzer production capacity. Today, many of the world's deployed electrolyzers are Chinese alkaline systems. Chinese manufacturers have aggressively driven down costs while expanding production capability at astonishing speed. And in industrial transitions, manufacturing scale often becomes destiny. This is another hidden reality many people miss. Energy transitions are not won purely through invention. They are won through manufacturing ecosystems capable of producing infrastructure at civilization scale. Factories matter, supply chains matter, industrial labor matters, standardization matters, learning curves matter. The country capable of manufacturing electrolyzers most efficiently may shape hydrogen deployment more than the country that invents the most advanced laboratory design. That is why alkaline electrolysis remains so dangerous competitively. It already possesses industrial momentum. But alkaline technology is evolving too. Modern advanced alkaline systems have closed much of the historical performance gap with PEM. Zero-gap alkaline designs reduce ionic resistance by minimizing the space between electrodes and diaphragms. Improved separator materials like zircon enhance conductivity while reducing gas crossover. Better coatings improve catalytic activity. Advanced control systems improve load-following capability. Some modern alkaline systems now achieve operational flexibility that would have seemed impossible 2 decades ago. And this creates another important Renewable Energy insight. The hydrogen industry often frames technology competition too simplistically. It assumes older technologies remain static while newer technologies improve. But industrial reality is rarely that clean. Mature technologies improve too. They benefit from manufacturing optimization, incremental engineering gains, operational learning, materials refinement, and economies of scale. Sometimes they improve quietly enough that the market underestimates them. That may be happening right now with alkaline electrolysis. Because while headlines focus heavily on futuristic next-generation systems, alkaline manufacturers are steadily improving cost structures, dynamic response, stack performance, and deployment scale simultaneously. And the longer this continues, the more difficult alkaline becomes to eliminate from the future hydrogen economy, especially under system stress. Because ultimately, the future of green hydrogen may not be decided by which electrolyzer technology looks best in isolated technical comparisons. It may be decided by which technology survives the brutal realities of industrial deployment. Can it survive supply chain shocks? Can it survive financing pressure? Can it survive utilization volatility? Can it survive maintenance realities? Can it survive global manufacturing competition? Can it survive infrastructure bottlenecks? Can it survive low-margin commodity economics? That is the real competition. And this is why alkaline electrolysis still matters so profoundly. It is not surviving because the industry lacks innovation. It is surviving because industrial systems reward survivability more than novelty. That is one of the deepest lessons in the entire energy transition. The technologies that reshape civilization are not always the most futuristic-looking systems. Sometimes they are the systems capable of integrating into real infrastructure, real factories, real financing environments, and real operational constraints. Alkaline electrolysis may be over 100 years old, but the uncomfortable reality is that much of the modern hydrogen economy still depends on it. And unless another technology can simultaneously beat it on durability, cost, manufacturing scale, financing confidence, supply chain resilience, and operational survivability under stress, alkaline may remain one of the defining technologies of the green hydrogen transition far longer than most people expect. If you are building, financing, or evaluating hydrogen projects and want to model alkaline versus PEM using real utilization assumptions, real electricity pricing, and real system economics, H2 Hub by Renee Energy provides the tools to analyze those trade-offs properly. The link is in the description. Because in hydrogen, the technology alone is never the whole story. The system around it decides whether it survives.